beats. In this video, we are going to look at what is called the quotient rule. And of course, this quotient rule is for derivatives. So let's see how this works. Okay. First of all, what are we trying to do here? We are assuming we got two functions, say f of x and g of x, and they are both assumed to be differentiable functions. Then our goal is to find this thing right here, the derivative with respect to x of the quotient of these two functions, specifically f of x divided by g of x. So what is the derivative of a quotient of two functions, assuming each function is differentiable? So we're going to have to figure this out. And that's what we'll do in this video. Okay, so similar to how we did the product rule explanation, let's just start with two functions that we know are differentiable here. Let's say f of x is x to the 7th and g of x is x cubed. Nice power functions. Then we'll go ahead and find the derivatives of each of them. So the derivative of f of x, which is the derivative of x to the 7th here, by power rule, 7x to the 6th. Moreover, differentiate g of x. Remember, that was the function x cubed. Differentiate x cubed, we get 3x squared. So then, what's the point of this? Well, let's just go ahead and take the quotient of the derivatives of the two functions. So remember, f prime of x was 7x to the 6th. G prime of x was 3x squared. When I take the ratio of those individual derivatives, I get 7x to the 6th divided by 3x squared, which simplifies to 7/3 x to the 4th. So right there, there's the quotient of the derivatives. But what about if we went ahead and found the quotient of the two functions first? So the quotient of the two functions here is x to the 7th divided by x cubed, which is x to the 4th. So if I differentiate the quotient of the two functions, that's the same as differentiating x to the 4th, which gives me a 4x cubed. And similar to how we went about doing the product rule, as we can see here, those two things are not equal to each other, right? And therefore, what it shows is that in general, the derivative of the quotient of two functions is not equal to the quotient of their derivatives. So now the issue becomes, well, what is the rule for the derivative of a quotient of two functions? So there's that statement again, right? This is not true in general. Derivative of a quotient of two functions is not equal to the quotient of the derivative of the functions in general. So like I said, what is this? What is this formula? How do you find the derivative of a quotient? Well, we're going to go through the limit definition of the derivative and see how this works. Assuming f of x and g of x again are differentiable functions, and in this case, we're not going to let g of x be 0 since it's occurring in the denominator. So also assuming g of x is non-zero here. Then we can just write the quotient of the two functions, f of x divided by g of x. Let's just call it some function. Let's call it, say, q of x for like quotient of a function. Then this will be differentiable because each one is individually differentiable and g of x is non-zero. So if I just call that a function and then I solve that for f of x by multiplying both sides here by g of x, then equivalently, this statement is the same as saying that f of x is g of x times q of x. And that is a product, right? F of x is the product of g of x and q of x. So by the product rule, which we've already established in a previous video, I can go ahead and find f prime of x here by applying the product rule, and this is what we get, right? G prime of x times q of x plus g of x times q prime of x. That's our product rule. And that's the derivative of f prime, or it is f prime. It's the derivative of f here. Now, if I go ahead and solve that for q prime of x, because remember, q of x was assumed to be f of x over g of x. And then we have this relationship between the derivatives f prime, g prime, and q prime. Well, q prime is going to be our derivative that we're after, right? Q prime of x here is the same as the derivative with respect to x of f of x over g of x. So let's see what we get if we just algebraically manipulate that equation right above and solve for q prime. So what do we get? Well, first, if I subtract g of x and, or if I subtract g prime of x times q of x, so look at my statement right up here, right? I'm going to go ahead and just subtract that term on both sides. That's going to give me this statement right there, right? F prime minus g prime times q is g times q prime. And if I then just divide both sides by g of x, I get this statement right here. Q prime of x is the same as f prime of x minus g prime of x times q of x divided by g of x. So how does that help us? Because see, we have the formula now for q prime, but there's a q sitting in there still. We want this formula to be strictly in terms of f's and g's and their corresponding derivatives. So remember, q of x right up there, if we just substitute q of x with f of x divided by g of x, like so, gives us the following. So here's where that q of x was. I just replace it with f of x divided by g of x. And then I'm just going to clean this up. So this next step right here, all I did was take the f prime and get a common denominator with g of x so that I could add the terms in the numerator. So that's why we see that appearing right there. And then I'll go ahead and add those like terms up. So this entire numerator here gives us down here the following: f prime of x times g of x minus f of x times g prime, just rearranging those two terms right there, all divided by g of x, and then that's all in the numerator, and then all that's divided by g of x. So, of course, by division of fractions, this g of x comes down below, and voila. We get that the derivative of the quotient of two differentiable functions, f of x over g of x, where g of x is non-zero, is this formula that we see right here: f prime of x times g of x minus f of x times g prime, all divided by g of x squared. And you notice the pattern here, right? The terms and the order of the terms in the numerator do matter because it's a difference. So whatever that function is in the numerator of my quotient, that's always the function I'm differentiating first, as we can see here. That's the positive term. And then times the g of x, and then minus the f of x times the derivative of the denominator function. It's always in that order. So there's our quotient rule. And just to state it one more time, quotient rule for derivatives. Write it down, take a picture, put it in the list of all the other ones we got so far. You got two differentiable functions, f of x and g of x, with g of x non-zero. Then our quotient rule is just as we said a moment ago. So we use the product rule to help us come up with the quotient rule. And now we have it. So now, what should we do? Well, we should probably try a couple of these just to see how it works. And that's what we'll do. So here is an example of finding some derivatives. So we'll do 3 of these here. Let's find this first derivative. The derivative with respect to p of the function p squared divided by e to the p. So p here is treated as the input variable. We got a function of p inside there, and it is a quotient. So we think of p squared over e to the p like some f of p divided by g of p. A quotient of two differentiable functions. And of course, e to the p is never 0, so we don't have to worry about that. So you kind of think, okay, well, f of p here is p squared, and we can think of g of p as e to the p. We know we need the derivative of each of these to apply the quotient rule, so I might as well just find the derivatives real quick. F prime of p by power rule is just 2 times p, and g prime of p is just e to the p, right? Now remember, this derivative here, let's just write the quotient rule again so we get it down. This is going to be f prime of p times g of p minus f of p times g prime of p, all divided by g of p, that function, squared. So we have all the different pieces now. Let's plug them in. F prime of p, 2 times p. G of p is e to the p, minus f of p, p squared, times g prime of p, also e to the p. And then g of p is e to the p, and we're squaring that in the denominator. So let's clean this up a little bit. We see there's a common factor of p e to the p in the numerator. P e to the p, I'll factor that out. Just make it a little more clean here. What's left over? 2 minus a p. And all of this is divided by e to the p squared. So we see that this factor of e to the p does cancel out here. And what are we left with as a result? P times 2 minus p over e to the p. So there you have it. There's the first example of using the quotient rule to find a derivative. That's how it works mechanically. But let's do a couple more just so we get a better feel of it here. Here's one. Derivative of the quotient x squared divided by x cubed plus 1. So again, we think of this as a quotient, because it is, x squared over x cubed plus 1. Think of it as some function f of x over g of x. And so we can think of the numerator here, f of x is x squared, and the denominator g of x as x cubed plus a 1. Now both of those are differentiable functions. However, we should note that this rule is not going to be true if x is negative 1, because that's where g of x is equal to 0. So whatever we're doing here in this whole process, we got to take note. X is not equal to negative 1 because g of negative 1 is 0, and that's a no-no, right? This rule only applies for when the denominator function g of x is non-zero. So we'll just note that, right? The rule will be true other than at that location. So let's do this quotient rule, and again, to do this, we got to find individual derivatives. Notice up here, f prime of x is just 2x, and g prime of x is just 3x squared, both by power rules. Then, what's our derivative here? All right, let's write the rule out again. The more you write it out, the more it's going to stick in your head. It's going to be f prime of x times g of x minus f of x times g prime of x, all divided by g of x quantity squared. And then we'll replace all our different terms here. So f prime, 2 times x, times g of x. G of x was the quantity x cubed plus a 1, minus f of x, x squared, times g prime of x. That was a 3x squared. And then all of this is divided by x cubed plus 1, g of x, quantity squared. So let's clean this numerator up, see if anything happens. I'm just going to multiply everything out and then collect like terms if there happens to be any. So multiplying out the 2x times the x cubed plus 1, I get a 2x to the 4th plus a 2x. And then minus x squared times 3x squared is a 3x to the 4th. All divided by, again, x cubed plus 1 squared. And as we can see, we do have like terms in the numerator, 2x to the 4th and a negative 3x to the 4th. So let's combine those. What do we get? 2x minus an x to the 4th all over x cubed plus 1 quantity squared. And why not? Let's just factor out the common factor of the x on top. to get x times the quantity 2 minus x cubed there, if I could write, all over x cubed plus 1 quantity squared. That's about as good as it's going to get here. You could factor, but there's not going to be anything else that's going to simplify once I factor out those cubics. So there you have it. There's another example of using the quotient rule. So we're doing pretty good here. We got one more example to look at, and I just want to finish off the video by looking at this example because this one's a little more involved. Now, why is this one a little more involved? Because, again, we have a quotient, right? We're going to differentiate this function of t with respect to t, this quotient function. But notice in the numerator here, my function in the numerator is actually a product of two functions. So when finding this derivative, we're going to have to use both the product rule and the quotient rule together, as we are going to see here momentarily. So let's see, let's think of this here. This function that we have given that we're differentiating, the t cubed e to the t over 5 plus t to the fourth. So that's a quotient, obviously. But the quotient itself has, again, that numerator function, which is a product of two functions. So first we can kind of think of this as some function f of t over the function, say, g of t here, where f of t is t cubed e to the t, and g of t is 5 plus t to the fourth. Notice that g of t is never 0 here for all values of t, so we don't have to worry about that. And then we're going to have to find their individual derivatives, right, again, to apply the quotient rule. So I'm going to do that. And to find f prime of t, notice that I am going to differentiate the function t cubed e to the t with respect to t. So there I'm going to use my product rule. So what does the product rule tell us? It's going to be e to the t times the derivative with respect to t of t cubed, and then plus a t cubed times the derivative with respect to t of e to the t. So then let's do that. First term gives us a 3t squared by power rule times that e to the t, and then plus a t cubed times e to the t. Or if you prefer, t squared e to the t times a 3 plus a t. So there's just my f prime, right? I need that within this whole process. Now g prime, we might as well find that too because we need it. G prime of t here is just a little more straightforward, 4t cubed. Remember my g's up here. So then finally we can start piecing together the puzzles here. So this derivative, again, is going to be f prime of t times g of t minus f of t times g prime of t all over g of t quantity squared. That's our quotient rule. And then, of course, f prime, we found we had to use the product rule. So let's replace everything in the puzzle here. All right, f prime, I'm actually going to use this form of f prime because we might have to collect like terms and whatnot and multiply things out. So that's going to be a 3t squared e to the t plus a t cubed e to the t. That's f prime times g. G is a 5 plus a t to the fourth. And then minus f of t, t cubed e to the t times g prime. G prime was 4t cubed. All of that divided by g. G was 5 plus t to the fourth, quantity being squared. So it's kind of a messy one algebraically, but let's go ahead and just multiply out the numerator and see if anything cleans up. So a little bit of algebra here. All right, first thing I'm going to do is multiply this out. Do like a FOIL, right? If you will. So let's do that. I'm going to get 3t squared e to the t times 5. So that's a 15t squared e to the t. And then I'll go ahead and multiply the t cubed e to the t times 5. So I get a plus a 5t cubed e to the t. And then I'll multiply the first two terms with t to the fourth. So 3t squared e to the t times t to the fourth is going to give me a plus 3t to the sixth e to the t. And then t cubed e to the t times t to the fourth is a plus a t to the seventh e to the t. And then finally, let's multiply out those right there. And that's just going to be a minus 4t to the sixth e to the t. And all of this is being divided by 5 plus t to the fourth quantity squared. So are there like terms in the numerator? That was the whole point of doing this. There is, right? There's these right here, t to the sixth e to the t terms. So if I just combine those, what do I get? 15t squared e to the t plus 5t cubed e to the t, and then minus a t to the sixth e to the t, right? 3t 6 e to the t minus 4t to the sixth e to the t gives us that. And then plus a t to the seventh e to the t, all of that divided by 5 plus t to the fourth squared. And then last thing we really could do is factor out a common factor, which here is a t squared e to the t. So I get t squared e to the t times the quantity 15 plus a 5t minus a t to the fourth, and then plus a t to the fifth. All of that divided by 5 plus t to the fourth quantity squared. And that's probably about as good as it's going to get here. And so that last one that we just did right now, right, that one is a little more involved because of the fact that we had the product in the numerator happening. But we can see that all the tools we have so far, we just apply them, go step by step, and then we'll get our result. So there you have it. There's our video on the quotient rule. We showed what it is, and then after deriving it, we did 3 examples to give you an idea, hopefully, to be able to go and do this on your own. So that's it for this video. Until next time, it's Math and Beats, and I'm out.